Hello. Hello. Am I audible to you? Okay, let's start the session. Good evening, everyone. I am Monica Mallela and I am one of the TA for this basic course on construction materials. Hope you are able to see my screen. See, we already know the outline of the course. The outline of the course is like it has been divided into two parts. The first part deals with the providing of basic information on structure and properties of construction materials, such as the structure of common materials, and we have seen some common materials like steel, concrete, etc. there, and types of bonds and mechanisms of damage and failure in materials. Like if you take an example of steel bars, we have seen the mechanism of damage and failure in different types of steel bars. And the second part deals with the introduction to different materials used in construction. So now we are in this second part, and we already dealt with many of the construction materials such as cement, concrete, etc. And now this is the week 7. Now we are going to see the content related to week 7. Okay. As like every week I'll be posing some 10 questions related to the week 7 content. So by looking into those questions we can also go through the content related to that. Okay. Basically the week 7 content pertains to pertains to iron and steel. Okay. So first the first question is, as the carbon content increases strength of the metal. See, why we are studying this iron ore, iron and steel? What is the importance of this study? See, for suppose if you take steel, we have steel rebars and some structural steel, right, which will be using it for this steel rebars will be used for the reinforcement. For reinforcement purpose we will be using the steel rebars, and the many types of structural steel like bars, plates, sheets, etc. will be using in day-to-day construction, right? So that's why here the importance is uh, this is one of the construction material which we'll be using in our day-to-day construction. That's why the study is important here. Okay. So we have already seen when we studied the basics of the when we are at the introduction stage, we have already seen in this mechanical properties and failure mechanisms of different metals and etc. We have already seen the difference between mild steel and high yield strength deformed bars, like which has high carbon content. We have already seen that comparison through this stress strain graphs, right? As you remember, if you can remember, the if you take this as the stress and this as the strain for mild steel, if you say take this is for mild steel, the stress strain curve for mild steel, and for let's say this is for HYSD, high strength deformed bars, high strength deformed bars, in which case the ultimate strength is higher, the ultimate strength or ultimate stress is higher in case of this HYSD bars, right? In case of HYSD bars, higher strength, right? Whereas compared to this mild steel, when compared to this HYSD, mild steel will have less strength than HYSD because of the presence of the carbon content, because of percentage of carbon content, we can see that there is an increment in the ultimate strength of the metal. But if you consider the ductile nature of the metal, then you can say if you compare this HYSD and mild steel, the ductile nature will be less in the case of, for suppose if you take the area under this graph for HYSD bars, you can say that here the toughness, you can say the area under this stress strain curve will be toughness, right? So in case of this HYSD, this area will be less, that means the toughness will be less. So when in mild steel, when compared with HYSD bars, the toughness will be less in case of HYSD bars. So if the toughness is less, you can say the ductility is also less. So now I think you can answer this question. As the carbon content increases, what happens to the strength of the metal? So the strength of the metal increases. For suppose in the place of the strength of the metal, if you take it as ductility, then the answer will be decreases. The ductility decreases and the strength increases. So as the carbon content increases, strength of the metal excuse me, hello. Okay, the strength of the metal increases and the ductility of the metal decreases when the carbon content increases. Okay. And see the percentage of carbon in cast iron. In this lecture, you have seen in this lecture, you would have already gone through the content of the week 7, right? So week 7 we have iron and its products, right? Iron ore and its products. In that, what are the products you have seen? Pig iron, cast iron, ductile iron, then wrought iron. This is iron and its products. Iron and its products, and these are differentiated by manufacturing process, percentage of carbon, and the composition of raw materials, etc. So based on this, we have all these classifications like pig iron, cast iron, ductile iron, and wrought iron. And in each one of the product, you will have different percentage of carbon. Here, the question is the percentage carbon in cast iron is. The percentage carbon in cast iron is 2 to 4%. In cast iron, the percentage of carbon will be 2 to 4%. Whereas if you take the case of wrought iron, there will be 1% lesser carbon content than this cast iron. So around 1 to 3% of carbon content will be present in wrought iron. And in ductile iron, as compared to the cast iron, in ductile iron carbon content will be less. Okay, so the percentage of carbon content in cast iron is 2 to 4%. Okay. crudest form of iron is. What do you mean by crudest form? We'll be saying crude oil. Like what do you mean by crudest form of any product? Crudest form is the unrefined form. The crudest form is the unrefined form. For suppose if you get a kind of iron from this iron manufacturing process, and if you take the product as it is without any refinements, then it is called as crudest form of iron. Crudest form of iron. The crudest form of iron here is the pig iron. The crudest form of iron here is pig iron. I have already shown you the list of the products like pig iron, cast iron, wrought iron, etc. Right? So here the crudest form of iron is pig iron. Okay. The crudest form is nothing but the unrefined form. Okay. And here in mild steel the iron content is about. Mild steel is what we have seen earlier, like when we compared this mild steel with HYSD bars. What do we understood? That when compared to mild steel, the HYSD will have higher strength but lesser ductility. Here the question is different. In mild steel the iron content is about. In mild steel the iron content will be more. In mild steel the iron content will be more than any other composition. The iron content will be more in case of mild steel. So in case of mild steel the iron content is 99%. That's why it is susceptible to corrosion. It is susceptible to corrosion. Mild steel is susceptible to corrosion. For suppose when you take the constructions which are exposed to very severe atmospheres, like very severe climate, like sea water or some effects of rainfall, etc., then you can see that the mild steel gets easily corroded. Because of the fact that it has very higher iron content. And another thing what will happen is, for obtaining this mild steel in the manufacturing process, what we'll be doing is we'll be subjecting it to higher temperatures, and for molding it into the shapes we'll be subjecting it to some mechanical process. So because of that thermal and mechanical process together, it will have higher energy stored in that. And when it is exposed to some these environmental effects like higher temperatures or some sea waters, or some sulfur containing water, etc., it what there will be some reversal of the reactions, and it will go to its crudest form of iron, like Fe2O3. That's why it is susceptible to more corrosion. So in mild steel the iron content is about around 99% of the around 99% of iron can be seen in this mild steel. Okay. And the ratio of Young's modulus of high tensile steel to that of mild steel is about. How we can find this Young's modulus? What is the process for finding Young's modulus? See, we have already seen the graph. Stress versus strain graph, and for mild steel this is for high yield strength deformed bars, and this is for mild steel, right? And how will be obtaining this Young's modulus? Young's modulus is nothing but the slope of the stress strain curve in its linear elastic region. What is the linear elastic region in this mild steel? This is the linear elastic region. That means linear elastic region is nothing but in that region stress will be directly proportional to the strain, and at the same time if you remove the load, on that particular metal, it will again it will again take the same path. Okay, while loading it will take this path, and while unloading it will take the same path in reverse direction. That is linear elastic region. So the slope of the stress strain curve in linear elastic region is nothing but Young's modulus. So here this is the slope of the stress strain curve for mild steel, and at the same time this is the slope for stress strain curve for high strength deformed bar. Okay, high strength deformed bar. So in both of the cases you can say the Young's modulus will be the same, because we are considering the Young's modulus in this linear elastic region. So here you can say that the both are same. So then if both the values are same, for suppose the Young's modulus of high strength steel and mild steel are same, then the ratio of which will become 1, right? When E of HYSD is equal to E of mild steel, then the ratio will become 1, right? So the ratio of Young's modulus of high strength steel to that of mild steel is about 1, because both are same, since we are considering the Young's modulus in linear elastic region. Okay, the stainless steel consists of in it actually the stainless steel consists of 35% of nickel. The stainless steel consists of 35% of nickel. And here the question is, thermomechanically treated bars have the advantage of higher. What do you mean by this thermomechanically treated bars? See, thermomechanically treated bars are, the bars will be subjected to higher temperatures while manufacturing, like the bars will be subjected to, for suppose the steel bars are subjected to higher temperatures, and then it will be quenched means it will be quenched in cold water. Quenching means it will be immersed in cold water. Okay, after immersing this hot metal in cold water, what will happen? You can mold it into required shape, and then it hardens, and then it hardens. Okay, this is one type of manufacturing of bars for getting more advantage. For suppose if you are uh, if you are about to choose some rebars for reinforced concrete construction, what is your requirement? Like, what are all the requirements the rebar should satisfy? It should have higher strength, and at the same time it should have higher ductility. For suppose for gaining higher strength, what we are doing, we are increasing the percentage of carbon content. But if you increase the percentage of carbon content, what is happening to ductility? It is getting decreased. So at the same time, for suppose if you take the case of HYSD bars, at the same time we are not able to get both the requirements satisfied, like higher strength and higher ductility. We have to compromise any one of the thing, like either we have to compromise higher strength for higher ductility, or else we have to compromise higher ductility for higher strength. But that's why we have come to this thermomechanically treated bars, wherein we have both the requirements satisfied. Okay, both the requirements satisfied in the same product, so it will have the advantage of ductility higher ductility as well as higher strength. That is the advantage of thermomechanically treated bars. That is the advantage of thermomechanically treated bars. Okay, and here are the list of some of the definitions, and the list one pertains to some of the what to say basic terms, basic terminologies, and the list 2 pertains to what is the exact meaning of the word here. Okay, so first one is ductility. What do you mean by ductility? What do you mean by ductility? Why we need ductile nature of steel bars in construction? What is the importance of it? See, if you don't go for ductile steel bars, what will happen? If the steel bars are brittle in nature, opposite of ductile, what will happen is, if you load it to some extent and without giving any warning, the bar will fail. If you take a brittle bar, what will happen? Uh, after the bar reaches some yield strength or ultimate strength, what will happen is, without any elongation or prior warning, it will fail, it will break. But in the case of ductile bars, what will happen is, even after reaching the yield strength, it will get elongated. It will not fail suddenly after reaching the yield strength. It will get elongated up to some it will get elongated. That means there will be a reduction in the area, there will be a reduction in the diameter of the bar, and there will be an increment in the length, but the bar will not fail. And because of this elongation nature, uh, we can get a prior warning before the failure happens. So that we can take some safety measures. That is the importance of making use of ductile bars in steel construction, in reinforced concrete construction. Okay, so ductility is the property through which the metal can be drawn permanently over great changes of shape without rupture. Without any rupture, it can be drawn into several shapes. Okay, and then comes the brittleness, which is opposite to this ductility. So brittleness is failure without warning. That's why we won't be going for this brittle uh, brittle metals in case of reinforced concrete construction. Okay, and tenacity is nothing but high tensile strength. Tenacity pertains to high tensile strength, and toughness pertains to absorption of energy at high stress without rupture. See, you can see the meaning of toughness as, but suppose if you take this is the stress strain curve and this is the ultimate strength. Okay, then the area under the curve is toughness. So toughness is the absorption of energy at high stress without rupture. Okay, we have seen pig iron as the crudest form of iron, and it will have lesser percentage of carbon content, and it will have more hardness than any other iron product. So pig iron has higher hardness than 100% pure iron. 100% pure iron. Pig iron has higher hardness than 100% pure iron. Ultimate strength of high carbon steel in Newton per mm square. Ultimate strength from the stress strain graph of high carbon steel. This is the high carbon steel. This is the ultimate strength point. Okay, for suppose if you take Fe415 bars, here the yield strength is nothing but this one. Yield strength is 415 Newton per mm square. But in case of this high carbon steel, the ultimate strength can be as high as 2000. We have already studied that in case of high carbon steel, because of the percentage increase in this carbon content, the ultimate strength will be increased and ductility will be decreased. Okay, so here the ultimate strength can go as high as 2000 Newton per mm square in case of high carbon steel. Okay, high carbon steel. So these are the set of questions I have taken related to this week's content, and now we can actually go through the lecture notes so that we can have a quick view of the concepts. Okay, see the outline of the of this week's content is iron ore, iron products and steel. This is one part, and the other part deals with steel reinforcing bars. The other part deals with steel reinforcing bars used in concrete structures and structural steel. Structural steel means nothing but this uh, like I sections, channel sections, steels, sheets, plates, etc. Okay, so this is the outline. Like till now we have seen the questions related to this week's content. Now we are having a quick overview of the week 7 content. Okay, so these are when it comes to the various iron products, here the list of the various iron products as we already discussed is pig iron, cast iron, ductile and wrought iron. These are the iron products, and when it comes to steel, this is steel reinforcement and structural steel. Okay, steel reinforcement is nothing but the reinforcing bars which we are using in this reinforced concrete construction. Okay, to take care of the tensile stresses. Okay, so iron ore we have to manufacture the from the raw materials we have to manufacture this iron, and India contributes to around 5% to the world's iron ore output. Okay, and Australia stands at the first. Okay, and this is the manufacturing process. Like iron is melted in a blast furnace. This is the real peak of this blast iron manufacturing setup. Okay, and this typical blast furnace can have a height of up to from 30 to 60 meters height. Okay, this is the blast furnace you are seeing in this picture. What we'll do is we'll have a stack of the raw materials like coke, iron ore and limestone. These are all the raw materials. Okay, these raw materials will be conveyed to the blast furnace through this conveyor belt, okay, and it will be dumped here. It will be dumped here through a hopper arrangement. Okay, it through a hopper arrangement, and from here there will be a passage of hot air gases, okay, hot air gases, so that the temperature inside the blast furnace will be increased. Okay, here at the entrance the temperature will be very high, and gradually the temperature will decrease, and at each levels of the temperature there will be different formation of different byproducts. Okay, and at the last there will be formation of molten iron, and before that there will be formation of some slag which will have lesser density. That's why it will float on this molten iron, and it will be taken out through the slag drain. Okay, and this is the molten iron. This molten iron can be molded into different shapes. Okay, this is the arrangement of blast furnace. See, here you can see the temperature variations inside the blast furnace. See, this is the opening through which we are pouring the raw materials, and uh, here hot air blast, there is a mechanism for this hot air blast. So at the point of this hot air blast, the temperature will be around 1500 degrees Celsius, and whereas if you go up, the temperature will be reduced. Here it will be 850, 700 and 250, and at each and every temperature there will be different reactions taking place. Okay, see, at a temperature of 700 degrees Celsius, what is happening is reduction of iron ore. This is 3 ions of carbon monoxide is reacting with one molecule of iron oxide, which gives rise to 2 moles of iron and 3 moles of carbon dioxide gas. Okay, this is the reduction of iron ore. This is the iron ore, and iron ore is reduced into iron and carbon dioxide gases, right, at a temperature of 700 degrees Celsius. After that, what will happen is this carbon dioxide reacts with the coke. Coke is the raw material which we are charging it into the blast furnace. Okay, so the molecule of carbon dioxide which is released at this temperature is getting reacted with coke at this particular temperature, and again it is giving rise to 2 molecules of carbon monoxide. Okay, carbon monoxide, and after that the in the raw materials there is limestone also, right, and at this temperature the limestone is getting decomposed, and from this decomposition there will be a formation of slag. Okay, calcium carbonate is nothing but CaCO3. CaCO3 is decomposed into calcium oxide and carbon dioxide. Okay, and this calcium oxide, when it reacts with sand, that is SiO2, it will there will be a formation of slag. Okay, CaSiO3, this is nothing but the formation of slag, and here at this temperature of 1500 degrees Celsius, hot air reacts with coke. Okay, hot air reacts with coke, and there will be a formation of carbon dioxide gas. Okay, and after that the molten slag will be formed, and here molten iron will be formed. Molten slag will have lesser density. That molten slag is nothing but some kind of impurities. It will have lesser density, and it will be floating here, and molten iron will be at the bottom, and we can take out the molten iron. See how the molten iron is getting poured into the molds, and then it can be casted into some molds, and that is nothing but pig iron. Like here the metal will be poured, and it will be distributed on either side, and it will be molded. Okay, or else it can directly modern pig iron casting mold. This is modern pig iron casting molds with conveyor belts. Here the conveyor belt will be moving, and the molten iron will be poured into the molds, and you can after cooling it you can obtain the pig iron cast. Okay, and the composition and key properties of pig iron are as follows. It will have 3 to 4% of carbon and 90 to 95% of iron, and traces of other metals such as silicon, manganese and phosphorus, and it will have hardness greater than this 100% pure iron, but it will have lower strength because of this porous nature. Okay, and it is not good for this high quality works. We will not consider this pig iron for this high quality works. Okay, and this is the cast iron. Okay, these are all the materials which are casted out of this, which are made out of this cast iron products and which are used in construction like laying of pipelines, etc. Okay. See, this is the manufacturing of cast iron. In the case of manufacturing of cast iron, this molten iron plus carbon will be poured into a mold. And in the mold we'll have this foundry sand. Okay. uh, in the mold we'll have this foundry sand. So in that we'll be pouring this metal, and after removing it from the cast, see, this is the example of a cast iron product, how it looks like. Okay. And when you go to the composition and key properties of cast iron, it will have iron and plus and carbon content of up to 4%, which is more than the carbon content of pig iron, and it will have higher strength, and it is corrosion resistant, but it is highly brittle in nature, because as you can understand, here the carbon content is more than the pig iron, so you can say the brittleness will be higher. So this is the brittle failure, cup and cone ductile versus brittle failure. This is ductile failure, cup and cone failure, and this is the brittle failure. And here in this graph you can understand, see, on x-axis you can see increasing order of carbon equivalent, that means the percentage of carbon, and on y-axis you can see ultimate tensile strength. Okay, ultimate tensile strength. As the carbon content is getting increased, what is happening? See, based on the carbon content, we and the different cooling condition, the metal is behaving differently. That means the percentage of carbon is having more importance on the properties of the metal. Okay. And this is another form of iron, which is ductile iron, and which is most preferred because we need ductile nature of the materials. Okay, so ductile iron is more ductile than gray cast iron, and the reason for this is, if you take the microscopic if you see the if you see the gray cast iron at microscopic level, inside it will have flaky graphite materials, whereas in case of ductile cast iron you will have spherical graphite materials. Because of the presence of this flaky graphite materials in gray cast iron, what will happen is, it will the brittleness will be higher. And it will be broken easily. This flaky graphite materials will be broken easily. But whereas in case of this spherical graphite, there will not be breaking of the spherical graphite particles. So it uh, it will have this ductile nature. Because of the spherical graphite materials, presence of the spherical graphite materials, it will have ductile nature. So that's why it is known as ductile cast iron. And this is another form of iron, which is wrought iron, and which has 2 to 4% of carbon. Like cast iron has 2 to 4% of carbon, but whereas wrought iron will have less than 1% of carbon, that means 1 to 2%. And it will also have this slag inclusions, like we have seen this mountain slag, right? In case of wrought iron, the slag will be included, that's such as silicon, phosphorus and sulfur, and because of that it will have a grain structure. Okay, that is the difference here. And wrought iron when it comes to wrought iron properties and products, it will have stronger and lighter. It is stronger and lighter than cast iron. Why it is lighter than cast iron? Because it is having this slag inclusions, which are lesser in density. That's why it is stronger and lighter than cast iron, and less harder than cast iron. Okay, and it will be used in this metal fence and other complex cast shapes. Okay. See, this is the microscopic level view of this uh, cast iron, ductile iron and wrought iron. In case of cast iron, you will have flaky graphite. In case of ductile iron, you will have globular graphite, and in case of wrought iron, you will have a grain structure. Okay, and this is what I have explained in the case of mild steel, why the corrosion is happening. It is because of the extractive metallurgy in reverse direction. The terminology is extractive metallurgy in reverse direction. That means it will again, by interacting it with oxygen and water molecules, it will again go to its first form of iron ore, and uh, which is more susceptible to this corrosion. Okay, see, effect of carbon content on properties of plain carbon steel. So effect of carbon content, on x-axis you can say the percentage increase in carbon content, and on y-axis you will see this ultimate strength, where see, if you can notice, in if the percentage of carbon content is increasing, this ultimate strength is increasing. Okay, and the brittle hardness is also increasing. But the ductility is getting decreased with the increase in carbon content. That's what we have discussed so far, right? And till now we have seen the concepts related to iron and its products, and now this is steel, uses of steel in construction. We are using it in various ways, like reinforcing steel, that rebar for concrete, and structural steel such as plates, bars, pipes, structural steels, etc., and cold formed steel such as struts, roofing, cladding, and fasteners like bolts, nuts, and washers, and some miscellaneous products. Okay, and some miscellaneous products. So these are the importance of the steel products. Like if you take the case of some reinforcing bars, there also you'll have different types, as we already seen this plain mild steel bars, which are hot rolled, and cold twisted deformed bars, and thermomechanically treated bars. So based on the uh, way of the manufacturing, the bars will have different properties, and which will have different uses in the construction. Okay, so this is the overview of the week 7 content, and if you have any questions related to this, you can feel free to ask now. If you have any questions related to the content or related to the questions which I have posted, you can feel free to ask now. Any questions so far? Are you able to understand? Okay then, if you don't have any queries right now, I am closing the session for today, and we'll meet in the next week with the content related to week 8. Okay. Okay then, thank you.